Hello, welcome to this lesson in the AC Circuit Analysis Tutor. The title of this lesson is opening up a new branch, a new discussion topic in this section of electrical engineering on three-phase electricity or three-phase power. We also call it three-phase circuits. So if you ever hear three-phase power, three-phase electricity, three-phase circuits, we're talking about the same thing. Now before we get into the topic of this lesson, which is what actually is three-phase electricity, I want to let you know that you need to kind of realize that when you get into three-phase circuits, a lot of people have problems with it because it gets confusing. It can get confusing quickly because previously we've done analysis with sinusoidal AC signals running around circuits, but in all of those cases we really only had one source, and so one stimulating source going through and flowing through the circuit to deal with. Well, in three-phase electricity, we're going to have multiple sources, and the difference between them is going to be the phase angle or the relationship between those input signals. And there's really good reason why we do that. We're going to discuss those reasons here in just a minute, but it can get a little bit overwhelming at first. So what we're going to do is take a methodical step-by-step process, where first in this lesson I'm going to tell you what is three-phase electricity. In the next section, I'm going to elaborate a little bit more on why three-phase electricity is actually useful, so that you can keep that in the back of your mind and you can realize as we do the math and crank through the pain a little bit, for lack of a better word, you'll know that when we come out the other end, why it's actually useful. And then we'll crank through every topic step by step. We'll talk about how to write down the three-phase sources, how to analyze the basic three-phase circuits, and we'll build our complexity from there. So that's our roadmap. It's going to be quite a long process, but I promise you, if you stick with me, it's not going to be hard, because once you get the basic information and basic knowledge and kind of work with me through the process here, then every step along the way is going to be pretty easy. So this lesson is what is three-phase electricity. I wanted a general section. I'm not going to write too much on the board. We are going to write a few things down. I'm going to unfortunately have to read you a few things. It's a little bit faster than just writing it all on the board. Three-phase power, three-phase electricity, is really good for lots of things, but it's really good for a certain subset of things that we use it for quite often. And this is the punchline here. Why do we use this stuff? It's good for the generation, the transmission, the distribution of large amounts of power. When I say large amounts of power, I'm talking about a power generating station, like a power plant or something. To get an enormous amount of power from point A to point B, it turns out when you work through the theory that it's efficiently done with three-phase electricity. And the details of why, you'll get into that as you study this stuff a little bit more, but just know that for high power, high voltage situations, it's often much easier and just more efficient to do it in a three-phase circuit arrangement. The next one is something I'll expand on a little bit more in the next section. It's very, very good. Three-phase electricity, three-phase power, very, very good at powering electric motors. And what I mean by that, when I say it's good at it, I'm saying is that a motor is a spinning object, right? So when you feed it with a single sinusoid, a lot of times you end up getting vibrations in the motor. And I'm actually going to expand on this a little bit in the next section. When you feed it with a single signal, a single sinusoid. But if you were to arrange a three-phase circuit, which we'll draw in a little bit, and then feed the motor with a three-phase motor with a three-phase circuit, it turns out that you end up with a lot less vibrations and a lot more efficient transfer of energy into the motor. So that's a really big deal. If you're building, anything from a compressor in a plant to a compressor on a tiny little refrigerator, which is a motor in your house, or anything with a rotating shaft where it's a heavy bit of machinery, not a tiny little motor, then saving on vibration is a huge thing. I mean, if you can make a car vibrate less, or a spacecraft vibrate less, or whatever vibrate less, that's a huge deal. So if there's no downside to it, then there's a very good reason to go ahead and use three-phase power to do that. Now, we're going to draw lots of sinusoids and stuff in a minute, but in a block diagram type of sense, what you have on the left-hand side is basically a block. We're not going to talk yet about what is inside of here, but we will. And this is a three-phase source. I want you to kind of get used to seeing this terminology. This phi here, this means phase. So when I say three-phase, I might write it out. I might also say three-phase, like three phi. It's a kind of shorthand notation. So that's a three-phase source. And then you have a block over here, which we don't know what it is, but it's probably a motor, for instance. We've been talking about motors. So this is a three-phase load, right? So again, it could be a motor, it could be something else. And instead of, in the typical case, when we have a single phase, usually you'll have those two lines. We've talked about how AC works in the past. So current going in, going out, going in, going out. We've been talking about that for a long time. But in the three-phase case, you'll actually have another connection between them like this. So you'll actually have three sets of wires. Now there's actually other things called neutral and other things. We'll talk about that a little bit later. I'm talking about from a block diagram point of view. You basically have three connections, and they are going to correspond to the three different phases of your source connected into the different terminals of the load, the three-phase terminals of the load. And we'll call this thing the three-phase line. Now the reason I'm drawing this hokey diagram isn't because it's a fancy circuit, it's because we are going to rapidly get into the situation where I'm talking to you about the line current, the line voltage, the three-phase line current. You need to know that that is representing the lines connecting the source to the load. We're also going to be talking about, obviously, loads, but we're going to talk a whole lot pretty soon about three-phase sources, how they're connected. There's different ways to connect them. There's a delta connection, there's a Y connection, there's other things that you can talk about. But for right now, don't worry if it's a certain kind of connection in here. All you need to worry about is there's three lines coming out, which is true of any three-phase source, and three lines going into a load. That's always going to be true. We're going to be drilling into the details inside of these blocks as we go through the lessons. Okay? Now, if you remember, when we talk about sinusoidal sources, we use phasors, right? So we have a phase angle, and typically when we're doing regular phasor analysis, the source just has a phase a 0 and it's not because it's special, it's just because since it's the source, it's kind of the natural reference for everything else in the circuit. You're driving the source, so you typically say that's a 0 phase. It just means that the cosine starts at the 0 point, right? And everything else is measured relative to the source. But now we don't have a single source. We actually have three sources. So because we have three phases, each one of these is basically a separate source driving out, but there's a special relationship between these sources. They're not just random, they're special. And the special relationship is that these sources have a very special relationship with their phase angles, right? So if you remember back to phases, if you have a phasor, you can have 0 degree, you can have 10 degree, 20 degree, 30 degree. It just means the cosine is shifting where it starts. But since there's only 360 degrees in a unit circle, really your phase angle can only go between 0 and 360 degrees. Of course, you can measure negative angles going the other way, but they can always be translated into a positive angle, 0 to 360 degrees, right? So in a three-phase circuit, the punchline here is that these phases are separated by, since there's only 360 degrees in a unit circle, and we have three phases, and we want equal separation in the phase angles, that's what I haven't told you yet, then you get 120 degrees. So 120 degrees is the separation between phases and between three phases. Right? So that's important. So it doesn't matter if it's later on we'll talk about it, if it's a delta source or a Y source or a delta load or a Y load or mix and match delta over here, Y over here, doesn't matter. These guys here, the three phases connecting source and load, are always separated by 120 degrees because a unit circle can be separated three ways in an equal fashion by 120 degrees. That's always true. So just remember it. So phase A, you might call it at 0, right? But that means phase B has got to be plus or minus 120 degrees away, and so on from that. And we're going to draw a lot more pictures to illustrate this point, but it's just important for you to know that each of these phases are separated from the other ones by 120 degrees equally. That is the special relationship that makes it a three-phase source. If this is 0 degrees and then phase 2 is like 25 degrees, that's not a three-phase source. It's not a balanced three-phase source. I should say it that way. We call it balanced whenever it's 120 degrees. I guess you could have a three-phase source that has unbalanced in the phase angles, but in practice we don't ever use that, at least not for typical applications. We're always talking about balanced three-phase circuits, almost always talking about balanced three-phase circuits where the phases are separated by 120 degrees with respect to one another. So let's go over here and illustrate that a little bit more. So the simplest case is we label the phases. We label them phase A, phase B, and phase C. And that's going to be universally true. Phase A, phase B, phase C. So for instance, this might be called phase A, this might be called phase B, this might be called phase C. So the voltage at phase A, or the voltage of phase A, the line over here that we're calling phase A, is, in general form, it's going to be some magnitude, Vm, times the cosine. This is not the phasor notation. This is just the time domain notation. Omega t plus some phase angle. But phase A, we're typically going to always call it 0 degrees because we have to have some reference. And we almost always take phase A to be that reference. Okay? So here, because it's 0 degrees, this is implied as the reference phase. Everything else is related to that one. All right? Now this is the time domain representation of this, and this means that the phasor notation would mean, let me go ahead and give myself a little bit of room here. The phasor notation, VA, is going to be equal to the magnitude at a phase angle of 0 degrees. Nothing rocket science here. I mean, we've been doing this for many chapters now. We have a time domain representation. It's a frequency and a phase angle with a magnitude. And we can transform that into the phasor domain, and basically we just know that the frequency is going to be whatever it is, so we don't have to write it in our phasor. We just keep track of the magnitude and the phase. The phase for phase A is always 0. That's what it's going to be in all of these problems anyway. Right? So then the question is, if this is phase A, what would phase B be? And we already said that the phases are separated by 120 degrees. So phase B is going to be the same magnitude, because we're talking about balanced three-phase circuits. So everything about these phases is the same. The frequency, the magnitude are the same. The only real difference is the phase angle between them is what's different. So we have the same magnitude times the cosine of omega t, and then I have to ask myself, what is going to be the phase angle of phase B? Now, we know it has to be different from phase A by 120 degrees. So we have a choice. We could say your first reaction actually would be to just put 120 plus 120 degrees there. But actually, initially in the problems here, you'll see why in a little bit. We're going to take phase B to be at minus 120 degrees. Okay? And I'm going to draw a picture to kind of help you with that. For now, just let me get through the rest of the lesson, and then I'll kind of explain a little bit more why. We don't call it positive 120 here, we call it negative. But anyway, phase B is separated by phase A by 120 degrees. It's just that we went in the negative direction. So this phasor is going to be, phasor B is equal to the magnitude at an angle of negative 120 degrees, right? That's what we're going to have. Now, if this is phase A and if this is phase B, then what do we do for phase C? What do we write down for phase C? Well, it's the same magnitude for all three, Vm, times the cosine of omega t, and then I have to ask myself, what's the phase angle going to be? Forget about looking at this right now. Just kind of go back up to the top. Well, if this is separated here by 120 degrees, but kind of in the negative sense, then this one also must be separated from phase A, again by 120 degrees. But since I've already gone the negative direction for phase B, the only other way I can go to still get 120 degree separation is to make it positive 120 degrees. Right? And then we write the phasor representation of that as phase C is equal to whatever the magnitude is at an angle of 120 degrees, like that. So I'm going to draw a phasor diagram to kind of show you how these are related to each other, so don't freak out too much. But I just want you to know that phase A is always taken to be the reference. Typically phase B is a negative phase angle relative to phase A, separated by 120 degrees. Phase C is, again, because everything's measured relative to phase A, it's 120 degrees but up. And that way, everything is separated by 120 degrees. But to show you more graphically, I'm going to draw something on the board called a phasor diagram to kind of show you this. It's really simple, but it's helpful. And you're going to actually find yourself, when we're solving our three-phase circuits down the road, when you have an actual circuit in front of you and you're trying to figure out the phase relationship, you're going to come back. I'm going to show you as I work these problems that we're going to be drawing this diagram that I'm going to draw in a second a lot. So it's not a hard diagram, it's just a useful concept. So what we're going to do is we're going to represent, we're going to call this a phasor diagram. Let me go ahead and write that down. Phasor diagram of this balanced three-phase circuit is what we're drawing, balanced three-phase circuit. So what we're going to do is we're going to write them all as phasors, if you remember back, can be represented as a vector, really as a rotating vector, but let's just draw it in the static sense like this. So this guy we're going to call VA, and we're going to call that the reference, right? And this is at 0 degrees. Why is it here? Why is it pointing? You got to kind of imagine, let me go in pink or something. Let me just kind of like refresh your memory that this is like an XY plane, I guess, like this. This is kind of goes like this, and I'm not going to cover up the arrow here, but it kind of goes through the other side. So you could think of this as being X, this as being Y, right? So why is phasor A lying on the axis like that? It's because when we come back here and we look at it, it's some magnitude at an angle of 0 degrees. So this is a coordinate plane where the angle of the vector is the phase angle that we're talking about, and the magnitude is the length of this arrow. So I could put Vm here. I guess let me go ahead and do that. I'll just put Vm here. It's the length of the arrow and the direction it's pointing. Phase A always points at 0 degrees. Now when we go over here, we said, well, phase B is the same magnitude, of course, but at an angle of negative 120 degrees. Now if you look over here, this arrow is pointing at 0 degrees. This is negative angle. These are negative angles going this way, and these are positive angles going this way. Remember all that stuff from trigonometry. So if you go this direction, this is actually negative 90 degrees. If you were to go all the way here, this would be negative 180 degrees, actually. We don't want to go that far. We want to go to negative 120 degrees. That's going to be right about there, because this would be a little bit too far. So basically it's 90 plus 30 more, right? 30 more degrees. So it's going to be about there, something like that. So let's go ahead and try our best to do what we can to make this a nice 30-degree angle from that y-axis there. And let's go ahead and draw it. It should be the same length. I'm not going to be able to get it perfect, but it should be about the same length, maybe a little shorter, like this. Okay, so this is going to be VB, right? And I'm going to illustrate on here, let me see if I can pick a different color, that the angle here, as measured going like this, is negative 120 degrees. Make sure you can convince yourself of that. So VB lies right here because we start as a reference at phase A, negative 120 degrees, that's where phase B is. The length of this, I think I drew a little bit longer, but you got to use your imagination. It's the same length of the vectors as we go here. It's a little hard for me to see since I'm standing off to the side, but I'm pretty close. Now let's look at phase C. Phase C is the same magnitude, but at a positive angle of 120, again measured relative to the reference, which is phase A. So that would be 90 degrees here. To get to positive 120 is going to be just 30 degrees past here. So if I were to draw that one, we go back to here. Let me see if I can do a good job of that. Try to make it a consistent 30 degrees or something sort of like it, sort of like the same length here. That's pretty close. And I'll call that V sub C. And just to remind you, this angle is positive 120 degrees. Now I want you to look at this diagram, and it's actually really powerful because when I look at this over here, I see 0, negative 120, positive 120, and I can tell sort of from the math that they're all separated. Well, let me put it another way. It's clear that B is separated from A by 120, and it's clear that C is separated by A from 120, but until you actually do math and subtraction, it's not totally clear how B and C are separated. For instance. But when you look at the diagram, you can very easily tell that A is separated by C by 120 degrees, A is separated by B by 120 degrees, but also, if you look at the angle here, if you got a protractor from this one to this one, you can see graphically that this is also 120 degrees also. So I'm going to kind of draw in a weird color. I'm going to kind of come out here and just kind of like do something like this. This is also 120 degrees. Kind of put a double arrow. So not only is A separated by B by 120 and A separated by C by 120, but also B and C by implied nature of the unit circle and 360 degrees divided by 3, and when you actually draw it out, B and C are also separated by, again, 120 degrees. This is why it's called a balanced three-phase circuit, because balanced three-phase circuit, because the magnitudes of these vectors are all the same. I tried to draw them the same. The phase angles are constructed so that they're all equally separated from each other. That is what makes it balanced, and that's ultimately what gives it its usefulness. Now, if you wanted to look at it graphically, you can kind of see that it's 120 here, but mathematically sometimes, you know, we like to prove things, even though I know that you know this is 120. You have to be a little careful though. If you want to figure out what the angle here is in between these vectors, your first gut might be to take the minus 120 and then subtract something like 120. But it gets a little confusing because some of the angles are negative and some of the angles are positive. So if you really want to prove to yourself that this is actually 120 degrees, here's how you do it. I measured this as negative 120. That's the convention we use. But I also know that negative 120 degrees, okay, if you add 360 degrees to that, you're going to, in other words, if you start from here and you go all the way back to where you are by adding 360 degrees to get a positive angle, you're going to end up with 240 degrees. So this angle down here, this one here, I label it as minus 120. That's our convention, but I also know that in terms of positive angles, it's 240 degrees if I were to measure it around like this. From this direction, it's 240. If you take 240 and you subtract the 120 from here, so you're dealing just with positive angles, is why I'm doing it this way. 240 minus 120, you can see is, again, this separation here is 120. So I'm just proving that to you. You don't have to do that ever again, but that's what I'm showing to you. So what I wanted to illustrate in this section is very simple things. Three-phase circuits are useful in rotating machines for less vibration. They're useful for very high voltage, high power applications. And they basically consist of a source and a load. And they're connected by what we call a three-phase line. So we're going to have line current, line voltages, source current, source voltages, load currents, and load voltages all throughout this class. And we're going to define all that stuff as we go. The unit circle can be divided into equal 120-degree pies, or sections. So we define each of these phases as being exactly the same magnitude, same frequency, just simply a separation in their phase angle. And so here we have 0 as a reference, and we have B as negative 120, and we have C as positive 120. And when we draw that out, we see that every phase is separated by a balanced equal number of degrees of 120 degrees. All right, one more thing I want to say before I leave, before we go to the next section and get into some more details. When we talk about this guy here, where the phase angle of B is negative 120, and the phase angle of C is positive 20. This specific arrangement where we've drawn it like this, where A is here, B is here, and C is here, I'm going to get into it in more detail. That's called a positive phase sequence. There's actually another phase sequence called a negative phase sequence. We're going to get into that later. So for those of you who know a little bit about three-phase power already, and you're like, well, he hasn't talked about negative phase sequence yet, just hang on a second. I'm just getting you used to this stuff. I promise I'm going to introduce negative phase sequence in a minute. It's not hard. I promise you that. But you will have problems that have positive phase sequence and negative phase sequence to deal with on top of everything else. So we're going to get there when we get there. I just want to make sure you know that this is most cases, most problems. You're going to have this positive sequence arrangement, and in some cases we'll have a negative sequence we'll get to in a little bit. So follow me on to the next lesson, and we're going to talk about a little bit more detail about why three-phase power is so useful for rotating devices.